Welcome to this technical explainer. Today, we are diving deep into the cohesive neural blueprint and exploring how we can resolve the limitations of current systems using MemGraphRAG's innovative memory-based multi-agent architecture. Let's start with the core problem, the GraphRAG Paradox. GraphRAG promises comprehensive multi-hop reasoning, yet in real-world question and answering tasks, it frequently underperforms compared to a naive vanilla RAG. Why does this happen? It comes down to a fundamental trade-off. While expanding the graph improves your recall and coverage, it destroys relevance and precision. This floods the large language models with noise, leading to what we call the relevance collapse. The root cause of this paradox lies in the isolated extraction trap. Traditional GraphRAG chunks documents and builds knowledge graphs using local information only. MemGraphRAG shatters this limitation by injecting a global memory system, creating a hierarchical graph that beautifully combines a global view with local details. When we rely solely on local extraction, we encounter three critical failure modes. First is thematic irrelevance. Without a global theme, the system captures meaningless, off-topic facts that drown out useful context. Second is logical inconsistency. Independent processing introduces semantic contradictions across subgraphs. Finally, structural fragmentation leaves key entities scattered and disconnected, preventing multi-hop traversal entirely. Let's look closer at these contradictions. They typically fall into three categories: mutually exclusive conflicts, like assigning two different birth years to Einstein. Temporal conflicts, such as confusing the timeline between U.S. Presidents Biden and Trump. And granularity conflicts, where birthplaces might conflict between a specific city like LA and a broader country like the USA. So, what is the resolution? Enter the MemGraphRAG architecture. This cohesive system operates in two phases: an offline phase for memory-based indexing graph construction, and an online phase for memory-guided retrieval. It orchestrates a multi-agent group, a three-layer global memory stack, and a hierarchical graph to perfectly align unstructured documents into actionable answers. Let's break down the first pillar, the three-layer global memory stack. At the top, the ontology layer stores abstract schemas and serves as the logical backbone. Below that, the fact layer stores concrete entity relation triples to enable multi-hop reasoning. Finally, the passage layer preserves the original text chunks, ensuring every fact is completely traceable to grounded evidence. Pillar 2 is the Multi-Agent Curation Society. This dynamic loop features three agents: an extraction agent that pulls schemas, facts, and passages into memory, a conflict detector that asynchronously scans for redundancies and semantic overlap, and a conflict handler that is triggered to adjudicate and resolve conflicting triples using the original textual evidence. How do we solve irrelevance? Through unified schema filtering. When an agent generates candidate schemas, they are held as pending and evaluated through a frequency filter. Only schemas that exceed a specific empirical extraction threshold are promoted to stable schemas. By filtering out low-frequency, one-off schemas, the graph is scrubbed of noise before it can ever corrupt the reasoning chain. To solve inconsistency, we use global adjudication. When a conflict is detected between facts, the conflict handler acts as a judge. It bypasses the graph and traces straight back to the passage layer. Because the passage layer acts as the absolute source of truth, the agent can reliably compare grounded evidence to merge or filter facts, rather than just guessing. To fix fragmentation, the system employs memory-guided bridging. Instead of leaving local extractions as isolated islands, the system utilizes shared stable schemas from the ontology layer and entity embedding similarities to physically bridge these disconnected graphs. The result is a fully interconnected knowledge topology ready for complex multi-hop traversal. Moving to the online phase, we start with structure-aware node initialization. When a user query comes in, the system performs parallel multi-layer retrieval across the ontology, fact, and passage layers. It initializes entity nodes based on semantic relevance, type nodes with hub suppression, a penalty to prevent generic nodes from overwhelming the graph, and passage nodes prioritized by high information density. Next is graph propagation using Personalized PageRank, or PPR. From a normalized starting distribution, the system iteratively propagates using a damping factor of 0.5 to limit semantic drift. Upon convergence, the system successfully extracts the absolute top K passages and top M entities, ranked by global importance, to feed directly into the LLM. This represents a massive architectural paradigm shift. Unlike traditional GraphRAG's isolated chunk-level extraction, post-hoc quality control, and fragmented connectivity, MemGraphRAG brings global memory-driven coevolution, active multi-agent adjudication grounded in raw text, and unified memory-guided bridging. It upgrades online retrieval from flat semantic search to structure-aware PPR. The results speak for themselves with clear empirical superiority. On the Generation Accuracy Impact Scorecard, MemGraphRAG hits an impressive 59.25% average accuracy across complex multi-hop datasets. It consistently surpasses state-of-the-art baselines like linear-RAG, hippo-RAG2, and light-RAG, proving that globally consistent indexing dominates isolated extraction. Furthermore, MemGraphRAG offers an efficiency breakthrough with zero compromise. While a competitor like light-RAG might take over 11 seconds for retrieval, MemGraphRAG operates near-instantaneously at just 0.061 seconds. By relying on lightweight personalized PageRank rather than computationally expensive real-time LLM reasoning loops, it achieves top-tier precision at practical deployment speeds. It also boasts universal adaptability. Think of MemGraphRAG as the ultimate graph constructor. If you replace the flawed native graph constructors of frameworks like MsGraphRAG, LazyGraphRAG, or hippo-RAG with MemGraphRAG's globally consistent graph, their performance immediately upgrades. Architectural integrity is vital here, every single module matters. Ablation studies show that if you remove conflict resolution, multi-hop reasoning breaks down. Without hub suppression, generic nodes cause semantic drift. And without the schema frequency filter, irrelevant noise floods the graph, dropping performance significantly. In conclusion, MemGraphRAG has set the new standard for complex reasoning. By abandoning isolated local extraction in favor of a persistent, globally maintained memory society, it completely resolves the fundamental flaws of graph construction. Through its three-layer global memory, collaborative multi-agent curation, and memory-guided retrieval, MemGraphRAG delivers unmatched accuracy, extreme efficiency, and universal adaptability. Thank you for watching.